Okay. Should be live now. But what I usually do is give it a couple minutes to see who pops in. I know usually we have our Southern Hemisphere contingents that pop in, so it'll be fun because you're like a local for them. Speaking of which, there's Les. Les is from
Hi, Les.
He's from New Zealand, so this will be fun. So yeah. Anyway, we'll give it a few minutes, and then I'll introduce you, and we'll go from there. I think I have.
Cool.
So how has it been down there? Speaking of, because you're going into what, winter?
It's winter.
Yes.
Yep.
Yeah.
So hydro lakes are full. There's been it was cold and clear across the country over the last couple of days. So it's all good.
My envy knows no bounds.
At all. It's getting
warm. So horrible here.
It's getting warm here, so I much prefer it to be a little colder. But,
Yeah, the southern ski fields have opened up, so all is good.
That's awesome. All right, looks like we got a couple people, so I will go ahead and do the official introduction. So, welcome everybody. Thanks for joining on our lovely project podcast, Space Weather Unplugged. Today we have a special guest, Mr. Andrew Renton. I don't know if I said that right, but he is the Senior Principal Engineer at Transpower, the asset owner and system operator of New Zealand's high voltage electricity. So this will be a fun conversation because most people that kind of get into the space weather stuff, the media likes to say that it's going to take the power grid down and we're going to go back to the dark ages and it's going to be like the end of the world. And we're here to kind of debunk some of that. And so hopefully this will help you guys understand more about the power grids themselves because it is kind of interesting. It's something that's been around and none of us really know how it works. So I find that kind of funny. It's like we use it every day, but none of us really know how it works. So anyway, I will hand this over to Andrew if you want to say anything. If you want to do it, add to the introduction or whatever, and if not, I can just hop into questions.
Well, first of all, no mai haere mai, tēnā koutou katoa, and lovely to be here with you all. Kia ora from New Zealand. Yes, we will talk a bit about space weather from a grid owner perspective. Remember, it is slightly coloured by where we are on the planet and our size and our geography, because there are many things that go into impacting the types of things you will see as a GIC event, as a grid owner, wherever you are on the planet, just for the same size event that comes on out. So I've got a few slides for you.
Right.
It's probably more than a few slides, but it will give you an idea about what grid owners do, and I hope they'll cover your questions, and then we can take some more questions later or something like that.
Yeah.
So
let's start there.
Okay, Mary Beth, why don't you let us know what people were interested in, and I'll think about whether or not I'll be able to answer them.
All right, yeah, first, looks like nothing in the chat right now, so we'll start with what I have, which is basically how do storms impact the power grid? That's like the basics, so let's just go into that.
Okay, well, I'll tell you what, I'll throw my slides up, and then hopefully as we go through, we'll be able to make sure that we will have done whatever you needed.
Right.
So we'll see if we can find
the share button.
Stash them for you.
There we go.
Share button. Are you up?
Yep, I can see it.
Looks good.
Perfect. Right, I better see if I should have set that to presenter mode first too.
Hey, it's all
you
good.
You still see that? Awesome. Right. So let's bust into this. So I'm going to give you a quick rundown. There's about 30 odd slides. We will bounce through quite a few of them, and we'll just stop on the really interesting ones that might have some content of note. Your key takeaways. Remember, there are no human health impacts on the ground. It's only a technical infrastructure problem. And the effects that you will see will vary from country to country. And wherever you are in the country. Like the impacts in one side of North America will be different to the impacts on the other side of North America. They'll be different to the impacts in New Zealand. They'll be different to the impacts in the UK. As a grid operator, we do design for these things, and we do it with everything else that we do as well. And the event will play out over different timescales for different people across your country. Probably some things that you won't necessarily have thought of that you might want to is GPS and navigation systems will probably be affected one way or the other. We're not thinking about the satellites actually necessarily dying, but there's that amount of energy that's coming into the Earth's ionosphere, which might cause some disruption to the signal. So Uber Eats might be off for that evening. We do take a whole, in New Zealand at least, just like you do in the States, we take a whole of government approach because we're essential lifeline infrastructure. So that kind of means we work with our version of your FEMA, which is our NEMA, and we work right through to the Department of Prime Minister and Cabinet, ODESC and everything else as well. And as part of this, we have a whole joined up working group here in New Zealand that involves the major loads, the transmission sector, distribution, and the major generators. And that's just so as we can have a coherent response to this type of event. Give you an idea as to who we are and where we sit in the planet. We're a long way from everybody. And that kind of casts what our approach to these things are. It's also just to let you know that this is just another hazard that we manage, right? So grid operators will handle various hazards. We handle volcanoes, we handle seismic events because we're seismically active here, tsunamis, and all sorts of other things. So this is just another event that we kind of plan and exercise for.
Alrighty.
To give you that context of where we are on the planet and how we fit, the geophysical location of us is the red version, and the geomagnetic location is the yellow version. This is really important because the impact that you experience at a given location is dependent on many variables, and one of them is how the geomagnetic field impacts your particular part of the world. And you can see that we are physically more alike where Spain is, but magnetically we're much closer to the poles. So a lot of the stuff you'll see or hear from me is the New Zealand context, right? So you're going to have to take everything you know yourself and put it into your context. So the world will be impacted, but it's very local in terms of how it plays out.
Okay, quick question. Are you trying to share a slide?
Oh, can you not see that?
I can't see it. Because I was like, oh, you're describing something, and I'm not seeing that image.
You've got your PowerPoint up, just not the slideshow.
Yeah. So see if it's...
That's really interesting. My apologies. Look, I'll stop that, because it said stop sharing. I will go back, and I will just do this for you and try it again. That's really embarrassing.
No, you're fine.
Stream.
It's perfectly fine.
Okay. Right. Let us try that again then, team.
Trust me, I mean, the amount of times I've messed things up on here, it's just... This is why we're unplugged.
Okay.
Awesome. Okay, there we go. All right. Now I can see what you're...
So can you see that now?
Yes. Yep.
How very odd. Okay, so I tried doing full screen and sharing. Don't worry about that. There you go. There's us.
Perfect.
I'll let you see that we're a long way from anywhere, and that's why it's something that matters. This is the one that you were mostly interested in, which is where we sit on the planet, right? So you can see geomagnetically we're much closer to the UK than we are to where we physically sit, which is more like Spain.
Okay.
Something that's different between ourselves is we do two roles in New Zealand just because of our size. We actually own the assets, but we also run the power system in real time. So we run, we schedule up the generation and run it all. But it is an open competitive market for generation and retail, but we like the conductor. We own the poles and wires, and we are like the conductor of the system. Just some boring stats about us, which we'll just skip over. You probably all know that the sun has an 11-year cycle, right?
Yes, yeah.
But the most interesting part is that these events can happen at any time, right?
Yeah.
So I was lucky enough to go to Space Weather Week in Boulder, and this was a cool chart from one of the team, and you can see that these events could happen at any time, most of them in the descending phase, which is quite interesting. Pretty pictures, but you know all about that. This is the one that really matters for you. So you probably all kind of get the idea that a coronal mass ejection is like the sun has a huge explosion and just throws off tons and tons of charged particles, billions of tons of charged particles in our direction. And when they impact the Earth's magnetic field, it's kind of like a large stress ball, right? It's a planet-sized stress ball, and we turn the planet into a large generator, right? So if you can imagine your elementary school physics, where you run a magnet across a wire, so a changing magnetic field across a wire makes a current flow, well, that's kind of what's happening at a planetary level. And it's just like any electrical circuit. It's the big wires going down to the ground, coming back through the ground and coming back up again. So and that happens wherever there's two transformers, right? So that's why we're worried at the transmission level. The effect will be noticeable everywhere, like you could measure it in all electrical circuits, like your distribution lines, the poles and wires down your street, but it will be so small that it won't impact anything. It's when these impacts are over a really large, long distance wires, which is why it's a transmission issue. Other places that you're going to be into will be impacts for you will be in the anything to do with positioning or communications, not so much your cell phone because it's line of sight and everything, but anything where you're trying to bounce things off the atmosphere, like HF radio, or if you're trying to get a signal through the ionosphere where it might normally be nice and smooth, so it would be like a pot on a stove and it's really clear when there's no heat on it, so you can see the bottom of the pot. But when you've got heat on and everything's bubbling in the bottom of the pot, you can't see the bottom anymore. And that'll be kind of what the atmosphere is like. So you might not be able to get a signal through reliably to satellites for either communication or time signals or something like that for positioning, say.
All right, one more. Can we try to get it in presenter mode again? Just see if it'll work.
Try once more, eh?
Yeah.
Let's try again.
Let's see if it'll...
Yeah.
And if it doesn't work this time, we'll just go back.
Okay.
Only because Les is asking if he could see it, because he could see it better in presenter mode. So we'll see.
Yeah. Okay.
See it one more time.
One more time, team. Let's see if we can get this into presenter mode for you. Sharing screen and presenter mode, entire screen 4.
And then if it doesn't work, then it doesn't work.
Yeah, sorry about that.
No, it's all good.
Sometimes the Zoom share screen shares only the actual desktop, but then the window for the presentation is separate for some reason, so it doesn't share that.
Yeah.
To add more confusion.
I know.
Yeah, that's right. So, let's try that one once more.
That was a good photo, though.
Yes.
Sorry, team. Have you still got something?
I got
So we're
something.
just seeing the PowerPoint.
Yeah, it's still in the PowerPoint.
Yeah. Okay. Don't know.
Okay, we'll just
Go
roll
on.
with it.
Hey, I've got these slides. That's really a talking point. Don't worry about it.
All right.
Magic trick is the last time you've actually seen these things, we didn't. None of us had like a grid, right? So everything that we all have today, we didn't have any of it, right? So that's something to take note of. So we've got down the bottom left corner, which will be a really real challenge for you, is a teeny tiny little hydro generator which we put in, which was our first one in 1886. And your horse and cart is the old line truck for the Niagara Power Company heading away in 1897 for the first of your really long distance lines, which was 42 kilometres in the day. So it's just to say that everything that you take for granted today has never seen an event of the magnitude that you're talking of. And that's kind of which you won't be able to see huge amounts of, but we've got data. Then there's down the bottom here, there's really small light blue stuff, which is 21 years from our GIC sensor suite, which we have across the network that we own. We had a green triangle was scanner, and we had some things for Hydro-Quebec, and then we got up into 2012. We had a CME event that missed Earth orbit by about 9 days, and we're kind of designing in New Zealand for a 4,000 nanotesla per minute field change event. So,
that's cool.
Cool.
Yeah, so we're actually up around that level because we're, it's all related to the country you are and where you sit on the planet. We're long and stringy. We got a large coastline. It's like 1,400 kilometres from one end of the country to the other, but we've got 15,000 kilometres of coast. We're sitting on a volcanic field because of the two plates coming together. So we've got some really high ground resistances in some parts and not in the other. So it all depends. And we kind of have a 50-year probability of a CME occurring. It's about 64%. That's kind of just a wee bit less than an alpine fault rupture for us, which is about a 75% chance in the next 50 years, or a Mount Taranaki eruption being about 30 to 50% over the next 50 years. So we kind of take all this kind of stuff into account and kind of like plan for it as such. Geomagnetic storm scales, it's just really to say that despite all the good work that NOAA does and everything else, the existing storm scales as a utility operator just don't work for us, right? Gannon was an extreme storm at just around 400 nanoteslas per minute as seen here, but it was a bit of a yawn really. So we're really only interested in when it's getting up around 2,000 nanoteslas per minute. And this kind of goes to how the event kind of plays out, right? You have an eruption on the sun, it's 150 million kilometres away, that takes like 8 minutes for light to get here, and you'll know about it over the next 1 to 2 hours as some of those proton bursts and stuff like that come through and start to impact your radio in the ionosphere. But the CME itself will take, anywhere from 14 to 36 hours to arrive. The only thing we do know is the bigger they are and the nastier they are, the faster they travel. And the 1972 event romped home in about 14 hours, 14.6 hours or something. So we plan here in New Zealand that the CME will arrive in about 12 hours. And the impact to radio and stuff like that, the further up the radio spectrum you go with disruption to it, the more of an indication it will give you that this is going to be a bad event. Because normally it'll only affect the lower frequencies around HF. It might come up to VHF, but as it gets further up the band, it will really start to indicate that this thing could be nasty when it arrives. Boring stuff that many events have occurred across the world, and we have lost the transformer in 2001, which is why we're so interested in it. Impacts are really around voltage stability, because these currents are like DC currents, and transformers are designed to handle AC currents, which kind of means that they will saturate. And when they saturate, they produce harmonics, and those harmonics cause reactive power flow, etc. in these units. So that could lead to voltage stability, which of itself is not completely fatal. It does mean you might be sitting in the dark, but it doesn't mean that anything is necessarily damaged. The one that we do worry about the most is that we don't cascade out to dark, and physical damage happens to transformers. Because that just takes a long time to recover from. A couple of weeks to replace a unit, and if you run out of units because it was a really bad event, then that's a challenge. The other item that might impact us is a maloperation of our protection and monitoring systems, and that's where we're interested in supply signals to satellites or the actual systems themselves not talking to each other anymore. This is just a boring chart about E fields, right? So this is when you convert all of those magnetic fields that are changing in the atmosphere to what is the voltage they're producing on the ground and how high it is, because the bigger the voltage across the ground, then the bigger the current that'll be pushed through the wires. And this just is a heat map that shows, depending on which event you choose and how you compensate for latitude, you'll get a different kind of heat map. And this is back to that, you've got to be really specific about what's going on. The version that works best for us against all of the measured data we have is the Rogers numbers, which just happen to be a bit worse than NERC. So everything that you hear from us, don't necessarily run around and say the sky is falling at home, because if you're down around Florida or something, you might not have a problem at all, or whereas further north you might. We do the same stuff that you guys do, which is for making these calculations, you need to know how the magnetic field is changing, how it produces the E field on the ground, and then you need to calculate the impact of your transmission system. So it's all the wires. So you need a really good model of all your wires and substations and transformers. And then you need to know about the ground conductivity. One thing that we've done differently to what you've done in the States is you've kind of got like 50 kilometre square sections that might work for you. We have pulled it down to 20 and sometimes down to 10 square kilometre bits of dirt, just because the resistivity of our ground changes a whole lot more than yours. And we've found some really interesting pockets, like the difference between Auckland, which is right at the top of the North Island, compared to the bottom of the South Island, 1,400 kilometres away. We have pockets in Auckland which are seeing currents flowing that are the same as what's happening down below in the South Island. And the reason for that goes to the fact that we've got two continental plates crashing into each other, one subducting under the other, and that means that there's these low resistance paths for these currents to flow, because Auckland, right at the very top of the North Island, just happens to be sitting on a volcanic field. So those currents come, that magma and those low resistivity paths magically appear up at the top. So we've used all those data and all that maths to basically calculate what all the currents would be in every single transformer. Remember, these events, you won't be able to see much of it, but each of these events is a time history. Think of it like a seismic wave that goes up and down and up and down. Mm-hmm. Every single one of them is unique, right? Absolutely every single one of them. If I go back to the 1972 event that occurred, which caused, magnetic mines to blow up in Haiphong Harbour through Vietnam, and people having issues with regards to thinking that the Russians might be coming or something for ICBMs coming in over the top, because the over the horizon radar wasn't working. For all of that event turned out to be not as bad as it could have been, just because a number of the CMEs coming in to start with were all positively charged, so they didn't couple very well with the Earth's magnetic field. But then they only had one that was southward facing. They estimate and back calculated that if all of those CMEs had been all southward facing, so that all the impacts were building on each other and linking more and more with the Earth's magnetic field, you would have seen something much larger, maybe 1,600 nanoteslas per minute, rather than the 400 or so that they actually saw. So every event is unique, right? We use that, though, to try and calculate what the temperatures in transformers might be. And we've used all of that information because we've got this high voltage direct current link that links the two islands together. So we've always been interested in DC currents, which means we've got sensors all around the place. So we currently have 97 GIC sensors across 32 sites now. And we monitor all of that for spill current from the DC system. So we've got quite a dense network compared to most countries. So we've been able to validate our models to a much higher accuracy than most. We've even had the luxury of using our DC link as a large test set, and we've injected large currents into the ground deliberately so that we can measure what's popping up where. So we have a good idea what should pop up where, and then we've actually tested that by using the DC as a really large test set. We've built operating plans. Now, this is a wee bit different to a lot of people. Traditionally, if you see a big GIC event coming, everybody will connect everything they can to the network, and that is to provide as many Earth references as possible and try and distribute the GIC across as many individual pieces of equipment as possible. From all of that other stuff that we have, what we've done is we've actually worked out that we can lower the total amount of GIC in the system and the absolute peak in the most susceptible units by being very selective with which circuits are connected or in service at any one time at a grid scale level. In effect, what we're trying to do is steer the GIC away from the most at-risk units and make it harder for it to flow through the system. So we can take about 20 or 30% off the top of any impact and maintain system security. And we've worked all that out with our academic partners, a whole bunch of validation and modeling, and then we've put it into our system simulator. So that's quite different. Do a lot of information and sharing with people, a lot of just creating new displays and stuff. And this is Gannon.
All right.
This is Gannon.
Yeah.
That might be of use to you for context. Not that you're going to be able to see this. Real shame. Anyway, magic trick.
Yeah.
Magic trick is with all of those sensors that we've got, 97 sensors everywhere. It's all the top traces. It shows every single sensor we've got. The country, we've got the magnetometers across it. And the key thing is that these things play out differently, right? So how does the magnetic field change above your country or the area of ground you're at? What is the resistivity or the conductivity of the ground? And what is the electrical connections, the transmission connections above it? And you need to understand all of that to work out what's happening in your system. And the key thing to take out of this is really that at the very top of the country, most of the activity occurred in the first few hours of the event, and then it went very quiet. And the blue dots and the blue trace, at the bottom of the country, it was completely opposite. There was about a 6-hour time difference. So the event came in, big spikes early on, and then it just quietened down. Whereas at the bottom of the South Island, it was very quiet to start with, and about 6 hours later, then we got the big spikes. So you need to understand to a granular level a lot of stuff, right, is all we're trying to say. That kind of flows through to some of the currents that we've got. All of this was, academically is very interesting because everyone says it cannot be. And then I take a very pragmatic approach as an engineer that says, because I'm just a power guy, right? I take a pragmatic approach to say, well, that might be true, but this is what I measured, right? So I can measure it. My academics and scientists and heliophysicists have now made models for us, and they're guessing a number, and I can measure the number within a few percent. So whatever it is true. So we need to just work out what the new rules are. And the key item in here is right down at the very bottom of the country, we were seeing currents of around 30 amps during Gannon. And at the very top of the country, up at the top in a place called in Auckland, we were seeing 30 amps as well. Now the distance between the two is 1,400 kilometers, but they were exactly the same currents, about 30 amps, 32 amps. And a wee bit north of the very bottom of the country at a place called Dunedin, about 150 kilometres north of the point closest to the pole, where your normal logic would say it should be less because it's further away. That's where we saw the highest currents. We were seeing currents there of 113 amps.
That's pretty.
After we'd done our switching mitigations and sequences.
Huh.
So it's like really reinforces the idea you need to understand a lot at a granular level to be able to predict where your worst spots will be. Just a magic little slide that says the predictions from our scientists said 103 amps and I measured 113, right?
Yeah.
If you're vaguely interested in what it all means from the control room, our after action report is on our website. You can go on there and type, Gannon Storm System Operator, and you can see what we did and what we learnt. And imagine if it happened today, like a Carrington event happened today. Our challenge will be, we'll know about it in 8 minutes because everybody sees it, right? That's the speed of light. And then we're kind of essentially blind until that CME arrives at the L1 satellite grouping of, SOHO, ACE, and Discoverer, where we've got actual measurements. Like we had Bree talk to us about, so she put on a presentation for a whole bunch of people here in New Zealand, and she worked through how SWIPSy do their monitoring and prediction and everything else. And she would be, and others would be poring over solar observing pictures about how big this CME was and how quickly it was expanding, and get some rough estimates of some parameters. But she was the first to admit that, that's their best guess, and they're essentially blind until we go past L1, where we get our first measurement. And unfortunately for us, that's just a bit too late for us to do anything about it, because it takes us about 2 hours to put the system into a safe state. And that's kind of what all that slide says. Is it's got a copy of our switching and sequencing plans, and here's a bit of a time history, which fundamentally says, big thing happen, we'll know about it pretty quick, and then we'll start the clock. We'll be listening to all the science advice and how much chatter there is, and everyone nutting off about how big it is and the biggest thing they've ever seen, etc. And we will have to call the ball kind of 2 hours out, and we'll just have to, decide, are we going to go and put our plan into place, because it takes about 2 hours to do the switching. It takes time to ramp down the geothermal power stations so that we can quickly restart them. It takes time for us to park up the black start stations. So if the system crashed and we needed to restart from the black start stations, so we want to put the system in the most stable configuration it can be, but that takes a couple of hours. And of course, the L1 satellite only gives us 15 to 30 minutes of warning. So, we have to make some big calls early on or not when we're riding through. Lots of work to do. We're working with Solid Ground, etc., to put one of their blockers in as a trial. So we're doing that. We're trying to understand the local impacts so that we can talk to the local FEMA officers and tell them these suburbs we think, or these areas or regions may or may not be impacted. And then there's the things we could do as a community, and I'm talking about as a wider worldwide community. New Zealand can go away and get a few more sensors in its part of the world, but really everybody, really would like, or to get any more certainty, we kind of need a bunch of satellites 3 hours out, right? That's kind of what we need. L1 just doesn't cut it really anymore. No. So if we could all work together, we've got Five Eyes partners. The equivalent in the industry and telecommunication space is the C5 partners. So, Australia, New Zealand, Canada, the US, and the Brits. We have the capability that we could all chip some cash in, and we could all get 3 hours of notice if we just, decided to get 3 hours worth of notice and put a satellite mission out there. There's a whole bunch of places you can get international references of, from Seagray and EPRI and NERC, and the British put out a really good item from the Royal Academy on systems that might be impacted. And then I have some questions for us all and some references. I can give you a copy of these slides for use at your will if you want.
Sweet.
But fundamentally, if you and your family have a plan for a snowstorm or a firestorm or flooding or any other natural disaster that might turn the power off, you've got a plan for space weather, right? So you're not going to be impacted at ground level, and you have a plan. And the items in there that you just might want to think of is that you're probably not going to have GPS or VHF radio, HF radio, etc., or positioning, timing kind of signals. They'll be very unreliable at best. So that's an item. And something we learned from Space Weather Week was a whole bunch of satellite repositioning movements took on because the Earth's atmosphere expanded from all the expansion from all the extra energy coming into it. And I'm just going to leave it. I'm just going to leave that there now.
All right.
Stop sharing. I romped through a whole pile of information, and you probably didn't see much of it, but it's all there for. We take this seriously. We plan for lots of stuff, but it is an area of developing knowledge, right?
Yeah.
It's something we learn from and practice and take note of. But if you are planning to use Uber Eats for that night, right, go home. You're gonna live
Maybe not.
I'd suggest not. You have to cater for yourself. So sit out, have a nice barbecue, have a barbecue outside, and
Disconnect.
watch the pretty lights. And just the lights might go off, but the lights will likely come back on again, right? So just don't stress about it.
Yeah,
Make sure the beer's pre-chilled in the fridge beforehand. It's probably the best.
Yeah, that's a good one too. Yeah, I guess it's that's the what I took away from Space Weather Week and stuff too is that like you guys have done a really good job of just preparedness on it. Like it's interesting, like when I first started learning about power grid stuff, I didn't even realize how the ground that you're on makes a huge difference. And then like looking at the maps of the US, like Minnesota in particular is more vulnerable than other areas because of the composition of the ground. And then when you went into how you guys are on volcanic rock and these plates, it's like you guys are really have stuff to deal with.
Yeah. So it's like we have benefits. There's pros and cons for being a small country where in 3 phone calls I can probably get to the Prime Minister, right?
Right.
So we don't have any money to spend on these things, right? But it does mean we can collaborate and be very agile, very fast.
Yeah.
And if I look at the states, there's like 3,000 power utilities in the states, right? And Nurk and Mark and the team do a fine job, but it must be just like really hard, like wading
Right.
through treacle in the states to get anything at a national level done, which, and you can kind of appreciate it, but it must be really challenging to write a national policy where maybe 2/3 of the country isn't really affected by it because the way that the magnetic field sits above that part of the ground isn't really a problem. The network isn't really dense in that part of the world, and maybe the ground conditions are pretty good. Whereas there'll be other parts where it's a really big issue for people. So,
Yeah.
big interest and
and
big
it's,
challenge.
It's just the uniqueness of just the situation in general. You've got Aurora, which is pretty set, defined at a latitude, and it's happening at a certain area. And then you've got these GICs, which seem to be not necessarily independent of latitude, but far less relevant than like something like the Aurora would be.
Yeah.
It's crazy.
Absolutely correct. And we see that for ourselves, that, physically we used to, historically we used to think we're like Spain, it won't be a problem, don't worry about it. And then we had lost the transformer in 2001, and we're going, well, how did that happen, and why did that happen?
Right.
We spent 5 or 10 years trying to work that out, and then it comes down to, until we've done a whole bunch of magnetotelluric surveys and everything else, we couldn't really start to work it all out. And then you find out that magnetically, not physically, magnetically, we're like the UK and Norway. We're not like Spain, which is where we sit, or somewhere between Washington and Florida, right?
Yeah.
Which is where we sit in the States.
Geographically, at least.
Yeah, right? That's right.
Yeah.
So, yeah, there's many, many more things. But there you go.
So I had one.
So-
Actually, Margaret had a question. How much do you depend on NASA and NOAA predictions?
Right. So NOAA, so it's all part of a large international effort between NOAA, ESA, UK Met Office, etc. So the two big players are both NOAA and ESA.
Okay.
NASA and ESA for providing satellites and locations. But then it's SWIPSI and the UK Met Office that digest that information and spits things out.
Okay.
Both parties publish their forecasts about what's coming in, etc. And then this is where we differ. We're interested in G-scale. We're interested in an estimate of the planetary change in magnetic field.
Mm-hmm.
But because of all the things that Christian was just saying, and you too, Mary Beth,
Yeah.
about understanding ground resistivity and the network that sits upon it, that's where it differs, right? So, yes, for the NASA and ESA to provide data. Yes, for NOAA and UK Met Office to say we're expecting these field changes. But from that point on, everybody's is a unique individual, right? And we have to ingest field change data and take that on board and then calculate our own numbers.
Okay.
So does that answer
Yeah.
that question?
I think so. And now I'm trying to
Cool.
think. So you pretty much went through all this. There was another one. Oh yeah. I was gonna ask you, what is like the worst kind of case scenario for you? Is it more like these longer term multiple CME events, or like one big CME? Like what would be worse?
So that kind of is really dependent on define big, right? So one, like if you were thinking of those Miyake scale events, which occur in history, go back 12,000 years, etc. One enormous pulse like that would probably be quite disruptive to a lot of systems, but I'm not quite sure. Nobody quite knows, right?
Yeah. That's
What
a fair point.
what we do know from everything that we've seen so far, though, is that, like with Gannon, that was 16 CMEs were launched, 6 were Earth directed, and they all kind of bashed up against each other as they came in. So, which is why we went from G3 to G5 real quick, even though it was a small G5. If you have lots of CMEs quite quick, one behind the other, and they're all southward facing, so you get a good coupling on the Earth's magnetic field, then the background GICs will be elevated at quite a high level for a long period of time, and then you'll get these spikes that come up often. So if you've got a high level in the background, that means everything is hot and never gets a chance to cool down. So the spike you need to tip something over the edge proportionally can be smaller.
Okay. Yep.
Right? So as if you just had one biggish spike, it will come in, it might cause your system to collapse from voltage because of all this reactive power flow, but nothing's burnt out, right? Because it never got hot enough, quick enough. Because these spikes take 2 or 3 minutes to go up, 3 or 4 minutes to come down. And to burn out a power transformer, it's all about time, right? Time at those big elevated currents. So if it's really short and really sharp, it can be quite high, and we're not really going to worry. But if you've got a really high background level, so everything's hot already, and then you get quite a large spike that comes in over the top that lasts, 4 or 5 minutes up, 4 or 5 minutes down, that might be enough to tip you over the edge. Everyone's unique.
Yeah.
But I would probably go for, if I've got quite a few in a chain and they're all southward facing, they're all relatively large, and then they get a really big spike, that's the one that would probably worry me more than just a single large spike.
That's kind of what I was thinking too. And just learning some of how this works. It's like, the the longer it stays in that more elevated state, you know, like you were saying, it doesn't take much at that point to push it over. So I think that was because all the other questions I had you pretty much covered. So like, I guess we could say it this way, because it would, like, the satellite operators don't like solar minimum because coronal holes are a problem, but with power grid, coronal holes really don't affect you much, right? Like, not at all.
No.
Because like
no. You've got your solar radiation events, and you got your radio events. That's all a bit disruptive, but for power grids, it's 60 hertz and it's 50 hertz. It's all fundamental stuff that we worry about, but it does just cause a bit of havoc when we're off for days or weeks, but we're not expecting necessarily days or weeks, unless it's a large Miyake event. But it's, but part of it all comes down to how much knowledge and how things change, right? So in 2001, when we lost the transformer, and we had some issues in 1989, and the 89 event was, North America had a bit of a hit for like 9 hours. We've learned so much more since then that when Gannon went through, which was kind of equivalent to Hydro-Quebec, maybe 50 nanoteslas down a wee bit, it was the biggest yawn you've ever seen as far as we're concerned. Lots of people running around, lots of people asking questions like, oh my God, is the sky falling? And are we going to sit in the dark? And are we going back to the dark ages? And we kind of sat there and went, well, probably not really, because we've done this over the last 10 or 15 years. So it's going to be proportionally a much bigger event before we're going to really start to worry about it. So
that's good.
So it was a bit of a yawn. No, there was no impact on our power system. We did a bit of switching and stuff like that, and then we monitored those currents. But even at 113 amps through those transformers, nothing happened. Nothing tripped off. All the lights stayed on. Everybody went outside, looked at the pretty lights in the sky, came back inside, went outside, took photos, uploaded them to Facebook. It was all, it was all fine.
That's the best kind of outcome. You don't even realize anything happened.
That's how you know things were done well.
Yeah, well, that's right. It does mean, of course, that for the previous 12 years, there was a lot of hard work that nobody knows about, right? And we just got on and did it.
That's pretty much it. I want to see if I have any more. Probably more my curiosity is because I know because Swipsy I think is looking at changing or updating the G scale, and I think that's something that is probably beneficial to you guys as well, because like once you hit G5, that's it, and it's like and you could have like a low level G5 or like a crazy level G5 or like but you don't really know. It's just, hey, this is it. So I'm assuming that's something you guys are looking forward to seeing.
Oh yeah, we submitted on that, and would just love a G5 scale. That we appreciate that there's going to be lots of people who don't want to change the G5 scale because it's very simple, right?
Yeah,
it's very simple to understand, 1 to 5. And there'll be a bunch of historic record. So everything's a compromise in the world, right? Mm-hmm. So my crude primitive suggestion would be leave G1 to G5 alone. Don't touch the historical record. It is what it is. And just add kind of like an open-ended scale. Think of it like the modified Mercalli scale for earthquakes, right? Mm-hmm. It goes higher than the Richter scale, and it's all about effect, right? And if you just happen in the future to find a really big event, you can always add a number on the end, right? But that means that we won't get hassled by the press and every other person who's panicking that the word from NOAA came out on the warning and then the alert that said, warning, extreme G5 event, the world will implode. And it turns out to be a Gannon at, 420 nanoteslas, right? So to help everybody's sanity, right, and to make sure you don't get out of bed for something that's going to be a yawn and you won't see many pretty lights, just have a G6 or a G7 or a G8 or a G9, some way of being able to say, yes, we've moved into the extreme range, but this is a very vanilla, boring kind of extreme one, and this is the one where you want to change of undies later on after the event has passed, right?
Yeah.
So that would be great. Yes.
Yeah.
Yes is the simple one. So.
Good. I think I haven't run into anybody yet that's like, no, except for like you were saying, except like for the historical records, because it can kind of mess with that a little bit. But
I mean, you could go to historically break them up into like something else,
Yeah.
like DSP, and put them into appropriate categories that are new from there. I think there'd be a way to redo the old type of events.
But even if you just had a date range, right? So from 20 to 30, or choose a date, don't care. From that date into history, it was done this way, and from this date we added a new top end of the scale. There's a rule. Everybody knows the rule. You know, it's just it is.
I think it would.
But there helpful. You
go. Well, I think that's all the questions I had. I'm gonna scan the chat real quick here and see if there's anything else. Because I think there was some commentary about, you know, collaborations with other countries and stuff, which seems to be there's a lot of that. It seems going on between. So.
Oh yeah. So we during Space Weather Week, just there was NERC, DOE, etc. from the US. The Brits were there, we were there. Everyone kind of tries to share information and knowledge, and the human race didn't get to where it is because of our big muscles and big teeth and big claws. We got there because of our brains. and the fact that we collaborate together, right? That's what got us to where we are today, and I don't see that changing into the future. So, there is an international bunch of people who do stuff on this.
Perfect.
Well said.
Yeah, well said. Well, so looks like everybody in the chat has appreciated your talk here so far. So thanks for coming on here.
No worries. My apologies that for some reason it did not screen share correctly. I will send you a copy of the PDF of that presentation, and then you can do with it what if anybody actually writes to you and says, I'd love a copy of that, or I'd like to see that slide, you can send it out to them. And
we'll have a links section after the fact too, so people can grab it as needed.
Yeah, because I think
sweet as.
Because I know
cool.
I know Les was asking about it. He's always interested in all this kind of stuff, so we'll make sure we get it for him.
Sure, not a problem at all.
But I guess on that note, I will.
Margaret wants to know, Andrew, who your counterpart is for Australia.
Oh yeah.
So Australia in the network companies, or Australia in their Bureau of Meteorology, because Australia has 7 transmission companies, so there'll be 7 others. So in New South Wales, you've got Transgrid and Ergon and Ausgrid, and then there's Powerlink in Queensland, and there's SA Networks in Victoria, Western Power in WA, and you've got who else? Electronet in South Australia, etc. So there are a number, right? We're only 5 million people. We're in a landmass the size of the UK or Italy, right? So that's why there's only one.
Yeah. Not a big deal for you guys.
Yeah.
No big deal for us. We can easily talk to everybody real quick and easy, but we're happy to collaborate with anybody who wants to.
I love it. Well, alrighty. Well, thank you. Now she's like, what about Tasmania?
Yes, that's Hydro Tas, right? So there you go. There's Hydro Tas. Just remember, they're the West Island. We have the North Island, Maui. We have the South Island, and we have the West Island, which is Australia, 2,500 kilometres away, and 3.5 hours on a plane ride. So,
All right. I think that is it. So again, thank you so much for coming on here and talking about this topic. Because like I said, it gets a lot of media attention. People always think that, all the bad things are going to happen. So it's nice to know that there are plans in place, and, it's going to take a lot to really cause some bad things to happen. So
we haven't seen bad yet.
Yeah, we haven't seen it.
Really the point.
Yeah.
So I think it's like you said, just have a beer and enjoy the lights.
Yeah, that's pretty much it, right? It's really interesting. I should have had on my presentation. There's all of these people who think the world's going to completely implode, right? There's planes falling out of the sky and all
right.
that. There's lots of books lots of novels, lots of stories, and they all seem to have people on the cover with planes falling and the sun blowing up. And everyone's carrying a gun. I have no idea why a gun works, but there you go.
Yeah.
It is that kind of thing. Just chill, everybody. It'll be okay.
Yeah, it'll be
Good
fine.
advice.
It's a storm. Like all storms pass, and there's a nice blue sunny day, after it's all happened.
And life will move on.
Yeah,
And life will move on.
and we definitely
That's right.
appreciate your hard work in keeping it that way too. So, like
Well, thank you very much.
yeah, because I know it's like I said earlier, it's like it's the best when you don't even know anything happened. So
Yeah. Yeah, and you kind of, there's a bunch of people in everybody's utilities around the world who work on these types of things all the time to make sure you never think about when I turn on the light switch or I try turn my router on my laptop, or you get a hot shower or a hot meal or a cold beer or anything like that. It just happens, and then you moan when it doesn't happen, right? That's
Right.
kind of like the nice spot for us. The more you don't think about us, the better it is. We've done our job.
it's like we like it that way.
Yeah.
All
Hey,
right.
it's been an absolute pleasure. If you do need anything at any stage in the future,
Okay.
just sing out, because we're only an 11-hour plane ride away, or a very quick Zoom call.
Right, exactly. Speaking of technology.
That's right.
All right. Well, I will end the
Okay, guys.
Yep, I will end it
Thanks a
on
bunch,
the
Andrew.
YouTube. So, thank you again, and we
No
will
worries.
see you. We'll see everybody next week.
All right, everybody.
No,
Bye.
mai. Ka kite.
Adios.